Hello everyone, welcome to the class. Today we're going to look at the foundations, logic and proofs, part 2 of chapter 1, predict logic. In this part, we're going to focus on the predict logic. We're going to look at the language of quantifiers, logical equivalence, nested quantifiers, and also how to translate from predict logic to English. So first of all, let's look at what are predicts and quantifiers. Propositional logic is the focus of the first part. However, propositional logic is not enough for all of the logics. For example, if we have the following sentences, all men are mortal, and then Socrates is a man. Does it follow that Socrates is mortal? How can we prove this? How can we represent this in the propositional logic? Okay, so here we need a new language that talk about objects and their properties and their relations. Okay, so here we introduce the predict logic. Predict logic uses the following features. First of all, we're going to have some variables in it. In previous propositional logic, we do not have uncertain parts, such as variables. But in predict logic, we can use these variables in it. Once we have a sentence with these variables, we call them predicts, okay? Such as px, mx. For example, px can be x is made of green cheese. Okay, so we don't know what is x right now. We also can have a new definitions called quantifiers. We have two quantifiers. One is the for all. Another one is the exists. So for all means that, for example, for all x, px, or there exists an x, px. So these are all the examples of using quantifiers. We're going to show you how to use quantifiers very soon. The propositional functions are a generalization of propositions. The propositional functions here are actually the predicts with the a x in it. So we have a x is variable, and there is a predict. So px is a propositional function. So x, which is a variable, can be replaced by elements from their domain. For example, we can say x, the domain of x is all the students in our class. Okay, so for example, for all x, px. Okay, so let's say pxx means that x is a good student. So that means for all the students in our class, the student is a good student. Okay, so just very simple example. Propositional functions can become proposition, okay, when their variables are replaced by a value from the domain or bounded by a quantifier. Okay, so two ways we can change the propositional function with the variable in it to a proposition, which is a declarative sentence, can be either true or false. So the first one is to assign this variable a value from the domain, and the second one is using quantifiers. So for example, if let's say px denotes x greater than 0 and domain to be the integer, and then we can easily see that p minus 3 is false, because p minus 3 is actually means minus 3 greater than 0 is false, and it is a proposition and is false. Second, p0 means 0 greater than 0. It is a proposition, but it's also false. Similarly, p3 means 3 greater than 0. It is actually a proposition and is true. Usually, the domain is denoted by a letter u here. So u is usually a domain, okay? Denote the domain. So u comes from the, you can think of u comes from the, think about a universal domain, okay? So that's u. or the universe we're talking about, the universe of our discussion, okay, which is the domain. One example of the U domain is integers. Okay, for example, in the previous example, the domain of discussion is integers. Let's look at examples of propositional functions and their true or false values. Let's say the R, X, Y, Z is this propositional function, and the U to be the integers for all the three variables. So let's find out the truth values for the following expressions. First of all, R2 minus 1, 5. So that actually means 2 plus minus 1 equals to 5. So what is the truth value for this expression? Of course, it's false. Okay, and you can also check for the following two assignments: 3, 4, 7, which is true, and x3z. Right now is because x and z are not assigned with any value, they are still uncertain, not determined, so it's not a proposition. You can also look at the second example, which is q, x, y, z is this sentence right here, and the domain is integers, and you can also tell the truth values. The first one is true, second one is false, third one is not a proposition, similarly. You can connect the proposition logic, which can carry over to the predict logic with same connectives. We have the and, or, not, implication, biconditional, if and only if, okay, biconditional, to connect these the predict logics. Okay, so such as you can see previously, px denotes x greater than 0. So you can connect these atomic predict logics or propositions after assigned values using the connectives. Okay, so you can see the first one is because p3 is true and p minus 1 is false. So true or false, okay, is actually true. Second one is false. Next one is false. And expressions with variables are still not propositions, and therefore they do not have truth values. For example, here, y, x, they are still not determined. You can also change the predict logic to proposition by using quantifiers. Okay, we will see later on how to use this. Let's look at what are quantifiers we have first. Okay, so there are two kinds of expressions. One is all, for all, the other is for some. For example, all men are mortal, some cats do not have fur. Okay, so these are kinds of meaning all, meaning some. So therefore we have two quantifiers. One is called universal quantifier. That means for all, the symbol is like this. It's like an A, but you turn it around like this. And the other one is existential quantifier, so that it exists. It's like this one is like E, but you turn it around. Okay. And then you can use quantifier with the predict logic. So here for this one, for all x, px. Okay, so that means that px is true for every x in a domain of discussion. Exist x, px actually reads there exists x, px. So that means for some x in a domain, px is true. So the quantifiers are said to bind the variable x in these expressions. Let's look at some examples. Okay, for all x, px is read for all x, px. Or you can say for every x, px. Okay, so you can try to read the expressions using the definition right here. So let's look at the first example. If px denotes x greater than 0, domain is integers. So what does this mean? So this means that for all integers, x integer x greater than 0. Okay? So which is actually false, because integers have positive, have negative. You can also try the other following examples to see after bind the quantifier with a variable, you can see the proposition logic becomes the predict logic becomes a proposition logic, and there is a true or false value. Next is existential quantifier. So this expression is read as for some x px, or there exists an x such as px, or for at least one x px. Okay. So for example, same example here, px still denotes x greater than 0, and u is the integers. So this expression means that there exists an integer x, and x is greater than 0. So which is true here. Okay. It is also true if you define the u as a positive integers. Okay. Let's look at the properties of the quantifiers. Okay. The truth value of the existential and universal quantifier bind with the predict logic and variables depends on both the propositional function px and also the domain. So you need to check to determine the true or false value for these two expressions. You need to check both the predict function px and also you need to look at the domain. For example, if the u is a positive integer and px is a statement x more than 0, then exists x px is true because there is at least one positive integer which is less than 2. However, if you change the quantifier to all for all x, it is false because it's not true that for all the positive integers x, they're all smaller than 2. Okay, so these are the examples. You can also check other examples for this. So basically, to look at the quantifiers and predict logic, you need to check both the propositional function and also the domain of discussion. Sometimes if you change the domain, you can change the true or false value. If you change the quantifier, you can also change the propositional function. You can also change the true or false value. To evaluate the true or false value, you can look at for the universal quantifier, you can think of that you're trying to loop through all the x variable inside the domain and check if every px is true. If at least one px is false, then the universal quantifier for all x px is false. To evaluate the existential quantifier, you need to loop all the x in the domain, and if at least one x px is true, then you can terminate the loop and you can tell it's true. If for all the x no px is true, then you cannot find a x for px is true, then there exists x px is false because you cannot find at least one or any x to make px true. Okay. Even if the domain is infinite, you can also think of the quantifier in this fashion. Okay. But sometimes the loop will not terminate, but you will think of other ways to prove that. Okay. So you can think of a logic trying to loop through all the examples to determine the px. And also later on, we can also use the mathematical induction to try to prove a statement if the domain is infinite. So we will cover that in the later chapters. So give an example, if the domain of U is finite, which only have 3 elements, 1 to 3, so to check for all x px, you can just look at p1, p2, p3 if they're all true. So we're going to use n here. So for existential, so it can be either p1 or p2 or p3, at least one of them is true, then this is true. So we're going to use the or here. the precedence of the quantifiers are actually higher than any other, all the logical operators. But in our class, and usually when we understand the statement, for example, like this, we always like actually mean this one. That means for all x, px, or qx. So this is by a natural understanding. So don't be confused. Okay. So how to negate the quantifier? Okay. So for example, for all x, jx. Okay. So how to negate it? So you can just think of this way, not for all x, jx. And if you move this inside, you need to change for all to exist, and then change gx to not gx. So the meaning is very simple. Okay, for example, for it is not true that all the students in our class has taken a mathematics class before. It is not true for every student in our class has taken a mathematics class before. The equivalent is actually means that there is at least one student in our class who has not taken the mathematics class. So this is a very simple example. Okay, so when you move the not across inside the for all, you need to change for all to exist, and then you can put the not in front of the propositional function. Okay, you can also try to make other examples, such as example like this. Try to understand it. Similarly, you can also negate the existential quantifier, and it's very similar. For example, this is for not exist x, jx, and then when you put this in the not inside, you need to change exist to for all, and then put not in front of a jx. Okay. So returning to the previous example, you can actually use in the following way to look at the expressions. So the two premises are for all x, x is a man. If the domain is all people, for all the people is a man, the people is mortal. If the people is a man, the people is mortal. And therefore, Socrates is a man. So therefore, Socrates is mortal. So using this way, you can see we can use predict logic to define, to derive this logical expression. How to define the equivalency in predict logic? So statements involving predicts and quantifiers are logically equivalent if and only if they have the same truth value. Okay? So that means for every predicts substituted into this statement, and for every domain and of discourse use it for the variables for the expressions. Okay. Oh, I'm sorry. So here it is for every domain of discussion. Okay, used for the variables in these expressions. Okay, discussion. So we use a notation S equivalent is T indicates that S and T are logically equivalent. Okay. For example, if you use a two double negation, that is actually equivalent with S itself. We also have De Morgan's laws for quantifiers. Okay. For example, if you put the not inside, we have this one. You have put not inside. We have this one. Don't forget to turn. If you put the not inside, don't forget to turn the for all to exist. Exist for all. Okay. So let's look at how to translate the English sentence into logic. Okay. Example 1. Every student in this class has taken a course in Java. Okay. So first of all, we need to decide what is the domain of discussion. Based on the domain you choose, you can have different predict logic expressions. So if we say that U is all the students in the class, and then define the propositional function Jx means that X has taken the course in Java, And then this sentence can be easily translated into for all x, jx. So that means for all the students in our class, this student has taken a course in Java. But if you change the domain U differently, that can be a different. For example, if you say U is all people, then you have to define another propositional function, Sx. That means x is a student in the class. So that means for all the people, x. If x is a student in this class, then x has taken a course in Java. Okay? Please be very careful here that if you change the implication to and, it is not correct. So you can try to ask yourself why it is not correct. Try to think of this question, okay? Because the meaning is different. So double check this example right here. So let's look at the same, another example, okay? So, but to change a little bit. So some student in this class has taken a course in Java. So how to translate this one into logic, predict logic? So same, let's decide what domain we're using. If we say U is all the students in the class, then this sentence can be easily translated, there exists x, jx, which is very simple. But if you say U is all the people, then we have to define same propositional function Sx, means x is inside this class. Okay, so for all the people, there exists one people, that this people is inside this class, and this people x has taken a course in Java. So that will be the same meaning as this one. However, here, if you change and to if then, it is not correct because the meaning is different. Okay. Another example, some students in this class has visited Mexico. Okay. So you can define similarly, which is very easy, right? So if the domain is all the people, mx means x has visited Mexico, sx means x is a student in class, then this sentence is expressed like this way. There exists x, sx, and mx. And then for the second example, you define every student in this class has visited Canada or Mexico. Here at the cx, denoting x has visited Canada. So this sentence becomes for all x. Okay, so x is a people. If x is a student in this class, then mx visited Mexico, or cx visited Canada.